In this question, an atom is given. It is assumed to be a sphere of radius small letter a, having a positively charged point nucleus of charge plus Ze at its center. The center of the atom have a tiny point positive charge. The positive charge at the center is plus Ze. This nucleus was believed to be surrounded by a uniform density of negative charge that made the atom neutral as a whole. Surrounding the central positive charge is a uniformly distributed negative charge all over the volume of the sphere, so that the total charge of the sphere becomes zero, neutral. That means the central positive charge is plus Ze. The rest of the whole negative charge distributed over the entire sphere will be minus Ze, so that the total charge will be zero. The atom becomes neutral as a whole. They're asking to find electric field of this atom at a distance r from the center in the following cases. R is greater than a, the point is outside the atom. R equal to a, point on the surface of the atom. R less than a point inside the atom. So first case, we are trying to understand case 1 and case 2 together, because that's something common for both. If you take a point outside the atom, the total charge enclosed will be zero, because it's given the positive charge is plus Ze and the negative charge is minus Ze. The total charge enclosed will be zero for a point outside. Not only for a point outside, even for a point on the surface, the total charge enclosed will be plus Ze plus minus Ze. The total charge enclosed will be zero. Since total charge enclosed is zero, the electric field intensity will be zero at a point outside the sphere or on the surface of the sphere. So case 1 and case 2, the electric field intensity is zero, because the total charge enclosed by the Gaussian surface is zero for r greater than a and r equal to a. Now case 3, the only difference is any Gaussian surface you take inside the atom r less than a, the total charge enclosed will have a contribution of single positive charge, which is Ze, and only a part of the negative charge. Complete negative charge will not be enclosed for the third case, because the radius is less than the radius of the Gaussian surface is less than the radius of the atom. It is zero only for r equal to a, and outside the total charge enclosed will be zero. So our aim is to find what is the total charge enclosed for a Gaussian surface with r less than a. One part is very clear, the positive charge will be plus Ze, and we have to find out what part of the negative Z is enclosed by the Gaussian surface. So the charge enclosed will be two contributions, plus Ze, which is the point positive charge, and part of the negative charge inside the Gaussian sphere of radius r. How much is the negative charge inside this Gaussian surface r? For finding that, we already know the volume charge density formula. Volume charge density is the charge by volume. So rho equal to the charge enclosed by the whole atom. Don't count the positive charge, because you already count the positive charge here. You're only counting the volume charge density of the negative charge, because positive charge is not distributed. It is concentrated to a single point. Negative charge is only distributed over the entire sphere. We are finding the volume charge density only for the negative charge. Rho equal to the total charge will be negative ZE, where the total volume of the sphere will be 4 by 3 pi AQ minus ZE by 4 by 3 pi AQ. This is the volume charge density for the entire sphere. Since it's uniform density, the volume charge density will be same for the entire sphere, or even a smaller sphere, or any type of sphere which is less than the radius of the atom, because the volume charge density will be uniform. Now the positive charge remains same. To find the part of the negative charge, we are using the formula charge will be volume multiplied by the volume charge density. The volume charge density into volume of the Gaussian spherical surface with radius r. We are using this formula for finding the charge as volume of the sphere into volume charge density. The volume charge density into volume of the Gaussian spherical surface. Volume charge density is already calculated as minus ZD by 4 by 3 pi A cube. Volume of the Gaussian surface will be just 4 by 3 pi R cube. So positive charge, this is a volume charge density. This is the volume of the Gaussian surface. We can substitute for the volume charge density as minus ZD by 4 by 3 pi. Now this is a total charge enclosed. We can cancel the 4 by 3 pi, 4 by 3 pi. Now this negative sign plus minus become minus. ZD into R cube by A cube. So taking ZD common out, 1 minus R cube by A cube. So this is a total charge enclosed by the Gaussian surface. Now normally we do every Gauss theorem application. We use the Gauss theorem as total electric flux equal to 1 by epsilon 0 times the charge enclosed for free space or vacuum. Now the flux can be EA cos theta. Cos theta will be 0 here because the area vector and electric field will be parallel to each other. So it will be E into area. Area will be 4 pi R square. That's a substitution for electric flux. 1 by epsilon 0 as it is. Then the charge enclosed will be ZD into 1 minus R cube by A cube. You can transfer the 4 pi R square to the right side. So you get the formula for electric field intensity. ZD by epsilon 0 1 minus R cube by A cube into 1 by 4 pi R square. So that's the expression for electric field intensity at a point inside the sphere. What maximum we can do? You can take LCM. So A cube minus R cube by A cube. Then just multiply 4 pi R square. It doesn't make a difference because all the values are unknown to us. Nothing is given as a numerical value. So you can finish it here. That's the expression for electric field at a point outside the, inside the atom. Outside is 0, on the surface also 0.